Welcome to The Explainer. Today, we're diving straight into something absolutely fascinating. We're demystifying the complex architecture behind the AI tools we interact with every single day. We're literally taking a journey inside the digital brain.
You know, it's a question that feels a bit like magic when you really stop to think about it. How does a computer turn billions of random, disconnected words into a conversation that feels entirely human? We just type a quick prompt, and seconds later, bam, we get a polished essay, complex code, or a highly nuanced answer.
To understand exactly how that happens, we first need to define what a large language model, or LLM, actually is. Basically, think of it as a wildly well-read, incredibly smart parrot. It's an advanced AI system that processes massive datasets to understand, generate, and predict human-like text. It literally learns to talk by listening to billions of human conversations, picking up on the underlying patterns, rules, and structures entirely on its own through unsupervised learning. When we zoom out to the big picture, the macro lifecycle of an LLM is essentially a massive pipeline. The journey goes all the way from collecting huge amounts of raw data from books and articles to processing those massive datasets, right down to generating coherent responses and continuously learning. It's a huge undertaking. But today, we're going to zoom right into what happens in the middle. We're looking inside that glowing digital brain at the exact moment you send it a query.
Section 1. Chopping words into tokens. How a digital brain reads a sentence.
See, humans read paragraphs, but computers, they only see numbers. So models use a process called tokenization, specifically relying on an algorithm called byte-pair encoding. Let's take the word supernova. The system first splits the word into individual characters. Then it looks at its training data to merge frequent adjacent pairs. Think of it like this. If it sees S and U grouped together all the time, it merges them. It keeps doing this greedily until no more merges can be made, creating these established subwords, and finally assigns a unique numerical ID to each piece. This is actually a huge deal because it helps models handle misspelled words brilliantly. They just break the typo down into known numerical token IDs, completely bypassing the spelling error.
Section 2. Giving words meaning, the magic of embeddings and power scores.
Okay, so we have numbers, but numbers alone are boring. Imagine giving these numerical tokens a rich recipe of power scores. Take the concepts for king, queen, and apple. The model scores them across countless different dimensions. But to keep it simple for our explainer, let's just look at royalty, masculinity, and food scores. King and queen? They both get a 9 out of 10 for royalty, meaning the LLM mathematically sees that they're very similar and should probably be grouped together. Meanwhile, apple gets a 9 out of 10 for food. These massive, multidimensional lists of power scores are called embeddings, and they are absolutely crucial because they give those plain numerical IDs a rich contextual meaning.
Section 3. Connecting ideas with attention. Shining a light on context.
So let's use a super simple sentence to set up our next problem. The king ate the apple. How does the model actually figure out the story here? I mean, how does it know who is doing the eating and what exactly is being eaten? Just lining up our meaning blocks side by side isn't going to cut it if we want the machine to grasp the actual narrative.
Well, the attention mechanism steps in to solve this exact problem. Think of it like a dynamic magic spotlight. When the model evaluates the word ate, it essentially shines a spotlight back on all the other words in the sentence to figure out the context. That spotlight shines super brightly on king because the embedding recipe for ate tells the system to look for a doer or a creature. It also shines really brightly on apple because, well, it's looking for food. This brightness is what we call the attention score, dynamically connecting the who to the what so the machine can build a complete, logical picture.
Section 4. Predicting the next word. Baking the context and dividing the pizza. Right before making a prediction, the model uses feed-forward networks, which honestly act a lot like an oven baking a cake. Imagine pouring all these token ingredients, both the really important ones and the unimportant ones, into a giant mixing bowl. The network takes these individual word recipes and bakes them into stable, context-rich concepts. So the word king is no longer just the abstract concept of a ruler. It specifically becomes the king who ate. Ultimately, the entire sentence collapses down into one final, highly sophisticated summary recipe.
And here is where it gets crazy. Once the baking is done, the LLM takes a deep digital breath and uses that final summary recipe to generate raw ranking scores, which are called logits, for every single word in its entire vocabulary. For a model like GPT-4, we're talking about over 100,000 words. A highly likely next word gets a massive positive score, while a totally out-of-context word, like car, gets a terrible negative score. But as you can probably guess, dealing with 100,000 raw, messy numbers isn't exactly efficient.
That is where the softmax function comes in for the grand finale. Imagine a bunch of friends trying to decide how to divide up a pizza by just shouting out random messy numbers based on how hungry they are. It'd be chaos, right? Softmax takes those raw hunger scores, the logits, and mathematically converts them into clean, simple percentages that neatly add up to 100%. For instance, the word he might get a 35% probability, full gets 25%, and so on. The model then picks the next word based on these clean probabilities, building out its response just one single word at a time.
But wait, does it always just pick the absolute highest mathematically probable word? Actually, no way. That's controlled by a setting called temperature, which basically acts as the model's creative knob. If you set a low temperature, the model is highly focused and predictable. It plays it safe, which is perfect for strict factual tasks. But if you crank that temperature up above 0.7, the model starts taking risks, selecting lower probability words. It suddenly becomes an out-of-the-box thinker, surprising, creative, and sometimes, well, completely nonsensical.
Section 5. Real-world impact and limits. Where LLMs shine and where they stumble. Because they can process vast amounts of context simultaneously, these transformer-based digital brains are unlocking some seriously incredible capabilities out in the real world. In healthcare, they aren't just writing generic emails. They are actively predicting protein structures and finding hidden disease patterns in medical records. In finance, they're instantly summarizing massive corporate earnings calls. Developers are using them to seamlessly write and debug complex software, and customer service is being completely overhauled by dynamic chatbots that hold genuinely helpful, context-aware conversations. It's a real game changer.
However, we have to take a step back and objectively look at the practical limits of relying on these probabilistic prediction engines. The hardware and operational costs to build and run these models are just staggering. They also depend on incredibly massive amounts of high-quality training data to function properly. And perhaps most famously, there's the big issue of hallucinations. Because the LLM is ultimately just predicting the next most likely token based on a mathematical recipe, it can generate highly confident, beautifully written, but completely inaccurate responses. It doesn't actually know truth. It just knows probability.
Which leaves us with a pretty fascinating reality to ponder. We've seen how these models chop text into numbers, find deep contextual meaning, shine spotlights on that context, and predict the future just one word at a time. As these digital brains continue to learn and evolve, moving from zero-shot learning to highly fine-tuned customization, what new capabilities and, honestly, what new challenges will they unlock next? Keep questioning, keep learning, and thank you so much for exploring the inner mechanics of LLMs with me on today's Explainer.